Bremsstrahlung, from bremsen to break, and Strahlung radiation, that is braking radiation, or deceleration radiation is electromagnetic radiation produced by the deceleration of a charged particle when deflected by another charged particle, typically an electron by an atomic nucleus. The moving particle loses kinetic energy, which is converted into a photon, thus satisfying the law of conservation of energy. The term is also used to refer to the process of producing the radiation. Bremsstrahlung has a continuous spectrum, which becomes more intense and whose peak intensity shifts toward higher frequencies as the change of the energy of the accelerated particles increases. Strictly speaking, braking radiation is any radiation due to the acceleration of a charged particle, which includes synchrotron radiation, cyclotron radiation, and the emission of electrons and positrons during beta decay. However, the term is frequently used in the more narrow sense of radiation from electrons slowing in matter. Bremsstrahlung emitted from plasma is sometimes referred to as free radiation. This refers to the fact that the radiation in this case is created by charged particles that are free both before and after the deflection that caused the emission. Particle in vacuum. A charged particle accelerating in a vacuum radiates power, as described by the Lama formula and its relativistic generalizations. Although the term Bremsstrahlung is usually reserved for charged particles accelerating in matter, not vacuum, the formulas are similar. Total radiated power. The most established relativistic formula for total radiated power is given by where is the Lorentz factor, signifies a time derivative of, and q is the charge of the particle. This is commonly written in the mathematically equivalent form. In the case where velocity is parallel to acceleration, the formula simplifies to where is the acceleration. For the case of acceleration perpendicular to the velocity, the total power radiated reduces to the total power radiated in the two limiting cases is proportional to or. Since, we see that the total radiated power goes as or, which accounts for why electrons lose energy to Bremsstrahlung radiation much more rapidly than heavier charged particles. This is the reason a TeV energy electron-positron collider cannot use a circular tunnel, while a proton-proton collider can utilize a circular tunnel. The electrons lose energy due to Bremsstrahlung at a rate times higher than protons do. Angular distribution. The most general formula for radiated power as a function of angle is where is a unit vector pointing from the particle towards the observer, and is an infinitesimal bit of solid angle. In the case where velocity is parallel to acceleration, this simplifies to where is the angle between and the direction of observation. Thermal Bremsstrahlung. In a plasma, the free electrons constantly produce Bremsstrahlung in collisions with the ions. A complete analysis requires accounting for both binary Coulomb collisions as well as collective behavior. A detailed treatment is given by Beekfy, while a simplified one is given by Ikimura. In this section we follow Beekfy's dielectric treatment, with collisions included approximately via the cutoff wave number. Consider a uniform plasma, with thermal electrons distributed according to the Maxwell-Boltzmann distribution with the temperature. Following Beekfy, the power spectral density of the Bremsstrahlung radiated is calculated to be where is the electron plasma frequency, is the number density of electrons and ions, is the classical radius of electron, is its mass, is the Boltzmann constant, and is the speed of light. The first bracketed factor is the index of refraction of a light wave in a plasma, and shows that emission is greatly suppressed for. This formula thus only applies for. Note that the second bracketed factor has units of 1/volume and the third factor has units of energy, giving the correct total units of energy volume. This formula should be summed over ion species in a multi-species plasma. The special function is defined in the exponential integral article, and the unitless quantity is a maximum or cutoff wave number, arising due to binary collisions, and can vary with ion species. Roughly, where EV is the Hartree energy, and is the electron thermal de Broglie wavelength. Otherwise, where is the classical Coulomb distance of closest approach? For the usual case, we find the formula for is approximate, in that it neglects enhanced emission occurring for slightly above. In the limit, we can approximate E1 as where is the Euler-Mascaroni constant. The leading, logarithmic term is frequently used, and resembles the Coulomb logarithm that occurs in other collisional plasma calculations. For the log term is negative, and the approximation is clearly inadequate. Beekfy gives corrected expressions for the logarithmic term that match detailed binary collision calculations. The total emission power density, integrated over all frequencies, is and decreases with. It is always positive. 4. We find the first bracketed factor has units of 1/volume, while the second has units of power. Note the appearance of the fine structure constant due to the quantum nature of. In practical units, a commonly used version of this formula for is. This formula is 1.59 times the one given above, with the difference due to details of binary collisions. Such ambiguity is often expressed by introducing Gaunt factor, for example in one finds, where everything is expressed in the CGS units. Relativistic corrections. For very high temperatures there are relativistic corrections to this formula, that is, additional terms of the order of 1. Bremsstrahlung cooling. If the plasma is optically thin, the Bremsstrahlung radiation leaves the plasma, carrying part of the internal plasma energy. This effect is known as the Bremsstrahlung cooling. It is a type of radiative cooling. The energy carried away by Bremsstrahlung is called Bremsstrahlung losses and represents a type of radiative losses. One generally uses the term Bremsstrahlung losses in the context when the plasma cooling is undesired, as for example in fusion plasmas. Polarizational Bremsstrahlung. Polarizational Bremsstrahlung is the radiation emitted by the target's atomic electrons as the target atom is polarized by the Coulomb field of the incident charged particle. Polarizational Bremsstrahlung contributions to the total Bremsstrahlung spectrum have been observed in experiments involving relatively massive incident particles, resonance processes, and free atoms. However, there is still some debate as to whether or not there are significant polarizational Bremsstrahlung contributions in experiments involving fast electrons incident on solid targets. It is worth noting that the term polarizational is not meant to imply that the emitted Bremsstrahlung is polarized. Also, the angular distribution of polarizational Bremsstrahlung is theoretically quite different than ordinary Bremsstrahlung. Sources of Bremsstrahlung. X-ray tube. In an X-ray tube, electrons are accelerated in a vacuum by an electric field and shot into a piece of metal called the target. X-rays are emitted as the electrons slow down in the metal. The output spectrum consists of a continuous spectrum of X-rays, with additional sharp peaks at certain energies. The continuous spectrum is due to Bremsstrahlung, while the sharp peaks are characteristic X-rays associated with the atoms in the target. For this reason, Bremsstrahlung in this context is also called continuous X-rays. The shape of this continuum spectrum is approximately described by Kramer's law. The spectrum has a sharp cutoff at low wavelength, which is due to the limited energy of the incoming electrons. For example, if an electron in the tube is accelerated through 60 kV, then it will acquire a kinetic energy of 60 keV, and when it strikes the target it can create X-rays with energy of at most 60 keV, by conservation of energy. A photon with energy of at most 60 keV has wavelength of at least 21 pm, so the continuous X-ray spectrum has exactly that cutoff, as seen in the graph. More generally the formula for the low wavelength cutoff is where h is Planck's constant, c is the speed of light, v is the voltage that the electrons are accelerated through, e is the elementary charge, and pm is picometers. This is called the Douinet-Hunt law. Beta decay. Beta particle-emitting substances sometimes exhibit a weak radiation with continuous spectrum that is due to Bremsstrahlung. In this context, Bremsstrahlung is a type of secondary radiation, in that it is produced as a result of stopping the primary radiation. It is very similar to X-rays produced by bombarding metal targets with electrons in X-ray machines, only it is produced by high-speed electrons from beta radiation. Inner and outer Bremsstrahlung. The inner Bremsstrahlung arises from the creation of the electron and its loss of energy as it leaves the nucleus. Such radiation is a feature of beta decay in nuclei, but it is occasionally seen in the beta decay of free neutrons to protons, where it is created as the beta electron leaves the proton. In electron and positron emission by beta decay, the photon's energy comes from the electron-nucleon pair, with the spectrum of the Bremsstrahlung decreasing continuously with increasing energy of the beta particle. In electron capture, the energy comes at the expense of the neutrino, and the spectrum is greatest at about 1/3 of the normal neutrino energy, decreasing to zero electromagnetic energy at normal neutrino energy. Note that in the case of electron capture, Bremsstrahlung is emitted even though no charged particle is emitted. Instead, the Bremsstrahlung radiation may be thought of as being created as the captured electron is accelerated toward being absorbed. Such radiation may be at frequencies that are the same as soft gamma radiation, but it exhibits none of the sharp spectral lines of gamma decay, and thus is not technically gamma radiation. The internal process is to be contrasted with the outer Bremsstrahlung due to the impingement on the nucleus of electrons coming from the outside, as discussed above. Radiation safety: in some cases, for example 32P, the Bremsstrahlung produced by shielding the beta radiation with the normally used dense materials is itself dangerous. In such cases, shielding must be accomplished with low-density materials, for example plexiglass, plastic, wood, or water. As the atomic number is lower for these materials, the intensity of Bremsstrahlung is significantly reduced, but a larger thickness of shielding is required to stop the electrons. In astrophysics, the dominant luminous component in a cluster of galaxies is the 107 to 108 Kelvin intracluster medium. The emission from the intracluster medium is characterized by thermal Bremsstrahlung. This radiation is in the energy range of X-rays and can be easily observed with space-based telescopes such as Chandra X-ray Observatory, XMM Newton, ROSAT, ASCA, XISAT, Suzaku, RESI, and future missions like IXO-2, and Astro-H-3. Bremsstrahlung is also the dominant emission mechanism for H2 regions at radio wavelengths. Quantum mechanical description: the complete quantum mechanical description was first performed by Bethe and Heitler. They assumed plane waves for electrons which scatter at the nucleus of an atom, and derived a cross-section which relates the complete geometry of that process to the frequency of the emitted photon. The quadruply differential cross-section, which shows a quantum mechanical symmetry to pair production, is: there is the atomic number, the fine structure constant, the reduced Planck's constant, and the speed of light. The kinetic energy of the electron in the initial and final state is connected to its total energy or its momenta via. Where is the mass of an electron? Conservation of energy gives. Where is the photon energy? The directions of the emitted photon and the scattered electron are given by. Where is the momentum of the photon? The differentials are given as. The absolute value of the virtual photon between the nucleus and electron is. The range of validity is given by the Born approximation. Where this relation has to be fulfilled for the velocity of the electron in the initial and final state. For practical applications, it can be interesting to focus on the relation between the frequency of the emitted photon and the angle between this photon and the incident electron. Car paragraph HN and Ebert integrated the quadruply differential cross-section by Bethe and Heitler over and obtained with and. However, a much simpler expression for the same integral can be found in and in. An analysis of the doubly differential cross-section above shows that electrons whose kinetic energy is larger than the rest energy emit photons in forward direction, while electrons with a small energy emit photons isotropically. Electron-electron Bremsstrahlung, one mechanism which is important for small atomic numbers, is the scattering of a free electron at the shell electrons of an atom or molecule. Since electron-electron Bremsstrahlung is a function of and the usual electron nucleus Bremsstrahlung is a function of, electron-electron Bremsstrahlung is negligible for metals. For air, however, it plays an important role in the production of terrestrial gamma-ray flashes. See also, cyclotron radiation, free electron laser, nuclear fusion, Bremsstrahlung losses, radiation length characterizing energy loss by Bremsstrahlung by high-energy electrons in matter, synchrotron light source, X-rays, history, list of plasma articles, references. Further reading, Eberhard and Werner Nakel. The Elementary Process of Bremsstrahlung. River Edge, New Jersey, World Scientific. P. A Scientific Lecture Notes in Physics, Volume 73. ISBN A981-238-578-9. External links, Index of early Bremsstrahlung articles.